Module 2. Remote Sensing in Agriculture. This module introduces the principles and applications of remote sensing technology in agriculture, focusing on the use of satellite and aerial imagery to monitor and manage agricultural systems. Learners will learn how remote sensing can enhance crop yield, improve resource allocation, and support sustainable agricultural practices. Introduction to remote sensing. Remote sensing is the process of acquiring information about the Earth's surface by measuring its reflected and emitted radiation without coming into direct contact with the object. In much of remote sensing, the process involves an interaction between incident radiation and the targets of interest. The most useful electromagnetic radiation in remote sensing includes visible light, VIS, near-infrared, NIR, and shortwave infrared, SWIR, to thermal infrared, TIR, and microwave bands. Passive remote sensing sensors record incident radiation reflected or emitted from the objects, while active sensors emit their own radiation, which interacts with the target to be investigated and returns to the measuring instrument. History and development. Remote sensing, a technology that has revolutionized our understanding of the Earth, has a rich history spanning over 2 centuries. From its humble beginnings to the current cutting-edge advancements, remote sensing has come a long way. Early beginnings, 1800s. The discovery of infrared radiation by Sir William Herschel in 1800 marked the starting point of remote sensing. The practice of photography soon followed, with the first photographs taken in 1839. J.B.L. Foucault's demonstration of the infrared spectrum in 1847 laid the groundwork for future innovations. Aerial photography, 1859 to 1916. The use of balloons for photography in 1859 and airplanes in 1909 expanded the possibilities of remote sensing. During World War I, aerial reconnaissance became a crucial tool for military operations. Radar and electromagnetic radiation, 1935 to 1940. Germany's development of radar in 1935 and the application of non-visible parts of the electromagnetic spectrum during World War II pushed the boundaries of remote sensing. Space age, 1950s to 1970s. Post-war military research and development led to significant advancements. The first space photograph of the Earth was taken by Explorer 6 in 1959. The launch of the first meteorological satellite in 1960 and Skylab's remote sensing observations in 1970 further expanded the field. Digital revolution, 1972 to 1986. Landsat 1 in 1972 and Landsat 4 in 1982 introduced digital image processing and new generation sensors, TM. France's commercial Earth observation satellite, SPOT, was launched in 1986, alongside the development of hyperspectral sensors. High-resolution imagery, 1990s. The 1990s saw significant advancements in high-resolution spaceborne systems and commercial developments. NASA's Earth Observing System, EOS, was launched in 1999, followed by IKONOS, offering very high spatial resolution sensor systems. Modern era, 1998 to present. The shift towards affordable, one-goal satellite missions began in 1998. Today, remote sensing continues to evolve, driven by technological innovations and growing applications in various fields. Basics of remote sensing. The amount of radiation that an object reflects is the physical basis of remote sensing. Special sensors collect information about the reflected energy, and processing facilities turn it into a format that anyone can use. This lets us learn about the object's unique properties that we wouldn't be able to see with the human eye. Objects and surfaces can be recognized and distinguished based on the radiant energy emitted, reflected by them. This principle underpins remote sensing, which detects and records the radiant energy for further study. Different objects and surfaces, like water, soil, or plants, return energy in different electromagnetic bands in different quantities. What factors actually impact this? Here are the main ones. Properties of the object. Chemical and physical composition, the kind of material, and surface roughness. Properties of the radiation, the radiant intensity, incidence angle, and wavelength. Diverse disciplines come together in remote sensing, including optical science, photography, spectroscopy, electronics, computer science, telecommunications, satellite launch technology, and more. And this is where the remote sensing system comes in, bringing together all of these individual technologies into one cohesive whole. Each of the many elements and stages in remote sensing must go off without a hitch for the process to be a success. Electromagnetic spectrum, EMS. The EMS is the continuum along which photons are located based on their properties. It also depicts a thermometer lying sideways, which demonstrates that as an object's temperature increases, the wavelength of the photons emitted decreases. This follows equation 2.1, which demonstrates that photons with shorter wavelengths have higher energy. A practical example of this would be that the majority of photons emitted from the Sun, 5,788 Kelvin, are around 0.5 times 10 to the minus 6 nanometers, while the majority of photons emitted from the human body, approximately 310 Kelvin, are around 10 to the minus 4 nanometers. These measurements are theoretical and are calculated using a theoretical object, often called a blackbody, that allows all energy to enter, no reflectance, hence black, and be absorbed, no transmission. The resulting EMR that is emitted would be generated thermally and be equal or greater than any other body at the same temperature. It is important to remember, however, that black bodies do not exist, and any real object will always emit a temperature less than a theoretical blackbody. E equals hc divided by lambda. Equation 2.1 defines the relationship between a photon's energy and wavelength. Visualizing the electromagnetic spectrum, EMS, in the figure certainly enables a wonderful comprehension of many concepts relating to photons. Perhaps more astounding, however, is the truth of how the faculty of human vision has incorporated these properties. The portion of the EMS that humans can see is between 400 nanometers and 750 nanometers, which correlates with the peak energy emitted from the Sun. Perhaps it should not be surprising, but of all the possible wavelengths emitted in our environment, human eyes have evolved to maximize solar photon emission. With a solid grasp of why electromagnetic radiation, EMR, is useful for remote sensing science, and how EMR is categorized along the EMS, we can begin to apply this core knowledge with ideas and applications related to practical use. As with radiation, there are a number of key terms used to describe the fundamental concepts that make remote sensing science possible. Some of the most common terms have been included below. They are organized into three categories: radiation basics, foundations of measurement, and methods of normalization. Our focus will be on methods of normalization, the three normalized measurements of EMR: reflectance, transmittance, and absorption. Each of these measurements provides useful information for understanding the interactions between EMR and the environment. Reflectance refers to electromagnetic radiation that has interacted with and been reflected by a surface. It has emerged as a popular method of evaluating a variety of environmental properties, including land use change, plant health, and plant diversity. Another popular normalized measure of the interaction between photons and a surface is transmittance. A photon that is transmitted has passed through the surface with which it interacted and provides insight regarding how much energy can reach other surfaces below. In a forestry context, this information can be particularly useful when determining the amount of radiation that reaches below the upper canopy. Absorption is a third, related measurement that refers to the amount of energy absorbed by the cells within a surface and is roughly equal to the amount of energy not captured as reflectance or transmittance. Equation 2.2. Absorptance equals 1 minus reflectance minus transmittance. Equation 2.2. These definitions allow us to start exploring a variety of remote sensing applications. In fact, most optical remote sensing techniques employ at least one of reflectance, transmittance, and absorptance to examine the world. This makes it the end of part 1 of this module. Stay tuned for the second part.